Hello, this is Dad. Today we'll be doing question 5 of 2021. So now we're doing triangular triples. So write down the values of f3, f4, f5 and f6. So let's write down x and f of x. So 3, 4, 5, 6. So f of x, 1, 1, 1, 1 triangle. So there are no triangles of perimeter 4 because flat triangle 1, 1, 2. However, there are 3 triangles. Actually, there's only one distinct triangle, but in 3 different orientations, so that counts as 3. And 6, there's only 1, 2, 2, 2. In ABC is a triangular triple, so that a plus 1, b plus 1, c plus 1 is also a triangular triple. So we have a plus b is greater than c. So a plus 1 plus b plus 1 is greater than c plus 1 by definition. So this means a plus b is greater than c minus 1, which is true. So there we prove this. So let's call this theorem 1. So in x, y, z is a triangular triple with x plus y plus z equal to an even number greater than or equal to 6, so that each of x, y, z is at least 2. Well, obviously you can do it the hard slot way, assuming that one of the sides is 1, and then, but we are going to do it something a bit easier. So 6 over 2, 6 over 3, since there are 3 sides, equals to 2. There, solved. And the x minus 1, y minus 1, z minus 1 is also a triangular triple. So this means 2 minus 1 equals to 1. So this means we are minusing all the sides by 1. So since each of the sides are greater than 2, greater than or equal to 2, all the sides in the reduced triangular triple will have sides greater than or equal to 1. So this means we are safe from degenerate flat triangles. Using the previous two parts, prove this. Now this might be a bit difficult because we are now going to use theorem 2. So using theorem 2, this triangle has perimeter 2k minus 3, and this is 2k. So there we have used theorem 2. So this means there are one-to-one correspondence between the triangles of perimeter 2k minus 3 and 2k. So this means you can match up all of them without any gaps. So we have actually proved it. So we can backcheck using theorem 1. So this means in this is a triangular triple. And this means this set is also a triangular triple. So this means it's also used theorem 1. So we are now considering a case where p is greater than 6 is even, and we will write p equals to 2s. So this means a plus b plus c equals to p. So let's just assume equals to 2s. At the very best, this p can be divisible by 3. So this means p over 3 equals to 2s over 3, which is strictly smaller than s. There, done. So for any a such that 2 is less than a less than s minus 1. Okay, I forgot to say this, but if it is equal to s, then you have this degenerate flat triangle of s, s, and then 0. For any a such that 2 less than a less than s is 1, show that number of possible values of b is a minus 1. So this means you can literally draw a triangle of these. So this means what you're going to do is that we're going to use a visual analogy. So let's just assume p minus a minus b. So this means so b can range 1, b, a minus 1. There, what does this mean? It also means that a will have more values to choose from, and therefore this will have a minus 1 choices. Hence give a formula. So this means we will use our sum of integers formula. So a minus 2 x equals to 1. So x equals to, we are now going to prove this. We are not going to prove this, but it's a minus 2, a minus 1 over 2. There, we have got f2a. And guess what this means? f21 equals to f24 equals to f twice 12, which is my age currently, equals to 12 minus 2, 12 minus 1 over 2. I will tell you that this answer is 55. There, we proved it. And now we have already accounted for all the triples with distinct orientation. You can make a table of them if you want, but we'll consider now the triples with not distinct orientation, where orientations are counted as undistinct, which means they are the same triangle. So this problem has already been researched, and the answer turns out to be the generating function of x cubed, or 1 minus x squared, 1 minus x cubed, 1 minus x4. Now you may be thinking, why are we putting algebra into a discussion of triangular triples? Because this sequence just has the property that if you expand it out and make it a Taylor series, which is basically a series of polynomials that will get you to this function, then the coefficient of x to the power of n in that Taylor series will give you the number of triangular triples with undistinct orientations with perimeter n. This sequence 0, 0, 1, 0, 1, 1, which results from this, is called Alcuin sequence. You can go research it up if you like, and even make a table with distinct orientations and with not distinct orientations. So have fun creating your own tables of triangular triples, and see you!